Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about the Swiss reluctance motor. We will continue from that. We understood that in a Swiss reluctance motor, the rotor is a slotted rotor and we are switching the stator current at positive dl by d theta to maximize the torque. So, this is a Swiss reluctance motor that we were discussing in the last lecture. So, we have a stator, we have the rotor. The rotor is a slotted rotor, does not have any winding. The stator has got the windings here, and for this example, we have taken an 8 pole stator A prime, P B prime, C C prime, D D prime, and a 6 pole rotor 1, 2, 3, 4, 5, 6 for our understanding. So, we have a 8 pole stator and 6 pole rotor, and we have few more parameters here that in addition to 8 stator poles and 6 rotor poles, we are also given with tooth to tooth pitch or pole arc to pole pitch is 0.4. It means 40% of the pole pitch is covered by pole arc. So, if we calculate the stator pitch, it will be 45 degree, because we have 8 stator poles, we have 45 degree is the stator pole pitch, and since we have 6 rotor poles, we have got 60 degree as the rotor pole pitch. 360 by 6 is 60 degree, and the stator pole arc, as we have already said, that 40% of the pole pitch is covered by pole arc. So, it is 0.4, pole arc to pole pitch is 0.4. So, the stator pole arc is 45 degrees into 0.4 is 18 degrees, and similarly stator slot arc, what remains is the slot arc is 27 degree. Similarly, rotor pole arc is 60 degree into 0.4 is 24 degrees, and rotor slot arc is 60 degree minus 24 degrees is 36 degrees. So, we can draw the diagram, the developed diagram, where we have developed the motor. What we have done is that the motor is a cylindrical motor. So, we have caught it and we have opened it. So, we have developed it in a linear fashion, so that we can see distinct pole and the stator pole and the rotor pole in a linear diagram. So, we have plotted here that the stator pole arc is 18 degree, stator slot arc is 27 degrees, similarly rotor pole arc is 24 degrees and rotor slot arc is 36 degrees, and the rotor is moving under the stator. So, it means the rotor is gradually moving under the stator in this particular fashion. So, the stator has got the windings, these are the stator windings, one of the winding is here. So, if you see this inductance of this winding inductance will gradually increase as the rotor pole arc will come under the stator pole arc, there is a overlap, and overlap will continue for 18 degrees, and then it will gradually increase for 18 degrees and it will continue up to 24 degrees, because 24 is the rotor pole arc, and then after that the trailing edge of the rotor will face the trailing edge the leading edge of the stator, and after that the inductance of the stator will gradually decrease. And we have also seen the variation of the inductance. This is a developed diagram here. So, the rotor is moving along this direction here, and the variation of the inductance is from a minimum value to a maximum value. This we can call to be L maximum. This is L maximum inductance of the winding of the stator. So, it gradually increases linearly up to 18 degrees, remains constant up to 24 degrees, then it decreases up to 42 degrees, and then it becomes low minimum value up to 60 degrees, and since this is a repetitive waveform, this repeats after 60 degrees. The same pattern is repeated here. Now, if we plot dl by d theta, the inductance variation with respect to theta, we see that from 0 to 18 degrees, we have the inductance which is constant, and from 18 to 24 the inductance dl by d theta is constant here, because the inductance is increasing. From 18 to 24 the inductance is constant, so the derivative is 0, and then from 24 to 42 the inductance is decreasing and the derivative is negative here. And these are the 6 degrees we have here. So, this we can have 6 degrees in this case, 6, 612, 618 and 24, 630, 636, then 42, and then we have 18 degrees more. This is 48, 54 and 60. So, the inductance dl by d theta, the derivative of the inductance is a something like a square wave with a intermediate 0, and what we are targeting here is that the current should exist only during the positive dl by d theta, so that the torque can be maximized. So, to ensure that, the switching has to be done appropriately. This is the main principle of the operation of the switched reluctance motor. So, we have a switching circuit in which this winding inductance is shown in this following fashion. So, what we want here is that the current should be only present during positive dl by d theta. So, when this switch T is made on, so the current flows in the circuit. So, the voltage here is positive, V is positive, this is plus VDC, and when T is switched off in this case and the diode conducts, this conducts, the current will continue to flow, it will flow in this direction. So, and hence the voltage VDC, which is the other side, we have center tapped connection here. So, the voltage V will be minus VDC. So, this is what we have presented here, and if we integrate the voltage, we get the flux. We see that the flux is a function of theta, theta is the rotor angle. And what about the current? The current is the flux linkage by inductance. The flux linkage is N phi by inductance. So, the current is a function of again theta. The theta is the rotor position here, is the position in this case, and as you go on increasing theta, flux will increase, and then as we increase theta here, current will also increase. But we will also note in this case that the current is inversely proportional to the speed. The current is also inversely proportional to the inductance. So, let us see how we switch the various voltages. If we draw the variation of inductance, the inductance variation is somewhat like this, is something like a trapezoidal signal. So, we are plotting this against theta. So, this is the inductance of the winding starting with 0, and we want that the current should only exist during the rising edge of the inductance. So, let us see the flux. So, the flux in this case, if you plot the flux, so the flux increases linearly, because we have applied voltage which is changing, which is constant, and it decreases like this. And what about the current? So, this is the flux. So, the flux is of this nature because we have applied the voltage which is positive, this is V and this is plus VDC by closing that transistor switch, and we open the transistor switch, we make the voltage negative. This is minus VDC. So, we have to make sure that before the onset of the trailing edge of the inductance, the current has to come down to 0. So, let us plot the current here. So, if you plot the current will be like this. This is our inductance which is rising. So, when the inductance is low, this is L minimum, and this is L maximum. So, most of the current will rise when L is minimum, because we have seen that the current is inversely proportional to the inductance. The expression for the current is given as N is equal to N phi by L. So, what is phi? If we simplify this, this is VDC theta by omega L. So, I is inversely proportional to L. So, when the inductance is very low, we have applied the voltage, current will rise to the maximum possible value. So, this is how the current will rise, and then when the inductance starts increasing, current rise will be, although we have a positive voltage in this case, the current rise will be little bit arrested. So, these are the various variables, the inductance, the flux, and then we have applied voltage in the winding, and this is the current. So, the current here, the rise is arrested because the inductance is gradually increasing. This is the increasing side of the inductance, and inductance is further increasing. So, we have to quench the current. So, to quench the current, we apply a negative voltage. Voltage is now minus VDC. So, the current will gradually fall down, and since we have a negative voltage here, the current will come down to 0 before the onset of minus dL by d theta. So, this is how the current will look like. So, we are switching appropriately, so that the current only remains during positive dL by d theta, and current is quenched before the beginning of negative dL by d theta, and this happens repeatedly in every cycle. So, since we are able to maximize the current during positive dL by d theta, the torque is maximized. So, if we see the expression here, what is the expression for the torque? Torque is equal to half I square dL by d theta. So, we have dL by d theta is constant. So, we can say here is equal to k into I square, because dL by d theta is constant during the rising edge of the inductance. So, the current is given by this equation. So, that is equal to, we can say that is k VDC square theta square by omega square, and since the current is mostly rising during L minimum. So, the current almost reaches the value when before the beginning of positive dL by d theta. So, this is the current which is here. So, this we can write here that L is equal to L minimum. So, this is approximately L minimum here, and I in this case during dL by d theta is equal to VDC into theta naught by omega into L minimum. What is theta naught? Theta naught is the advance angle. This angle is called the advance angle. So, theta naught is known as the advance angle. It means we are applying the voltage in theta naught in advance of the commencement of positive dL by d theta. Before the inductance starts rising, we are applying the voltage VDC before theta naught. Theta naught is the advance angle. So, this is the expression for the torque. Now, we see here that if this is the torque that we have here, this is the expression for the current. Now, we have low speed and high speed. When speed is low, current rises very quickly. So, we have to limit the current. So, the converter is operated under the chop mode. So, we have the mode of operation, modes of operation here. So, one is low speed. During the low speed, what we do, since omega is low, current I rises quickly, and therefore, the converter has to be operated in chop mode to limit the current. So, what we do here is that the current rises very quickly. So, we have to limit it within a band, that is called chop mode. So, this is the chop mode. We have the current which is rising very fast. So, the voltage is repeatedly applied and removed. So, we go on applying the voltage, and the voltage is applied and removed. So, that the current operates within the chop mode. So, it is basically contained within a band. And when the speed increases, if you see this equation, the current no longer increases quite fast, because speed is becoming higher and higher. So, if the speed increases higher and higher, to keep the current constant, we have to increase the advance angle. So, with increase of speed or at medium speed, let us say, advance angle theta naught is controlled to keep the current constant. So, we have this equation here, that to keep the current constant, we have to increase theta naught in conjunction with omega. So, as the speed increases, theta naught is also increased to keep the current constant. So, if theta naught is increased, the current is kept constant, but the power in that case will also be constant. So, what is the power here? Power here is T into omega, that is equal to k V d. Approximately we can say that this is equal to theta naught here. So, k V d square theta naught square divided by omega into L min. So, in this case, what we say that the power is approximately constant, because we are keeping I constant by increasing theta naught. So, we will be dividing our operating zone, our operation into a few zones here. So, the zones are as follows. So, this is torque versus the speed, and we choose a base speed here, omega base. So, we keep the current constant, current is constant by chop mode, this is the torque, and we are also plotting here current. this is our current, and we are also plotting advance angle theta naught. So, theta naught is kept constant. So, we are operating under the chop mode. So, this mode is called current chopping mode. And after that we increase theta naught, advance angle is gradually increased to keep the current constant. So, if we are increasing the advance angle to keep the current constant, so what we get here is this, that I is kept constant here. So, T omega is kept constant. So, the power is given by, so this is theta naught here. So, this is theta naught square. So, we have the power is kept constant. So, in this case this is constant power. Or T omega is constant, and this is also called advance angle control, advance angle control. Advance angle is increasing, however, torque decreases, torque will decrease, but the power will remain constant. After that the advance angle reaches the maximum possible value. So, we keep the advance angle constant here. Beyond this the current will decrease and the torque will further decrease. So, this region is called T omega square is constant. So, we have the modes of operation of a Swiss reluctance motor. So, initially below the base speed we keep the torque constant by operating in a chop mode, and then we increase the advance angle, the torque decreases, but the power remains constant, and beyond certain value of theta naught, because theta naught is gradually increasing. So, we have maximum possible advance angle. So, beyond the maximum possible advance angle is kept constant at the maximum value. So, this is T naught maximum, we cannot increase it further. So, if we keep the advance angle constant and still increase the speed, the current will decrease, and since the current will decrease, the power will also decrease. So, power will also decrease. So, in that case the power will decrease. So, T omega square equal to constant. So, this is the principle of Swiss reluctance motor. So, we have converter which will make sure that appropriate voltage is applied at the winding of the stator. So, by controlling the converter we can operate in various modes, thus we will be able to control the torque of the Swiss reluctance motor. And as we have already discussed that this motor is used for space application, because the rotor does not carry any winding. So, next we will be discussing an important set of drives which are used for traction application. So, what do we mean by traction drives? Let us discuss about traction drives. So, our next discussion will be on traction drives. So, by traction drives we primarily mean electric trains. This is one class of drives, and then we have electric buses, trams and trolleys. So, electric trains are basically for higher power. When we talk about electric trains, they operate in megawatt, and typical rating of an electric train is something like 6000 HP or more. On the other hand, electric buses, trams and trolleys are for medium and lower power applications. Nevertheless, they all use traction motors, and the nature of the torque speed characteristic are somewhat similar. So, let us discuss the drives which are used in electric trains. Now, if we consider these electric trains, we have the trains, they basically run on fixed rails, they run on fixed rails. And we have two types of trains primarily. One is a main line train and the other is a suburban train, or we can call those as metro trains. So, we have the main line trains, they are basically for long distances, and we have suburban trains, or metro trains, they are for short distances. Usually for long distance trains, we do not have frequent start and stops. The number of stops are limited. On the other hand, in suburban trains or the local trains or metro trains, there are number of starts and stops. So, we need to accelerate and decelerate the suburban trains more frequently than the main line trains. So, we will be discussing first about the main line trains. In the main line trains, what we have, the supply systems are as follows. So, if we talk about the supply systems, supply for electric motors, we can have the overhead transmission line, overhead transmission lines. In electric locomotive, so we have electric locomotive in which we supply primarily from overhead transmission lines. For the main line trains, and we have the diesel generator in diesel electric locomotive, diesel electric locomotive. So, for the main line trains, we have two kinds of supplies. Either we can supply the power from the overhead transmission line, or we can have a diesel generator, and the diesel generator is run by an IC engine, and the diesel generator gives electricity for powering the electric motors. But finally, in all these locomotives, the motive power which drives the wheel is an electric motor. Why electric motor? Because the electric motors can accelerate smoothly, the speed control is smooth, there is no gears, there is no changing gears, and it can be controlled very easily. We can reverse it easily, we can also brake without any difficulty. So, the motors are primarily electric motors. Now, if we talk about the overhead transmission lines, the diesel generator, they have high running cost. So, this class of locomotive have got high running cost, but low capital cost, low capital cost. On the other hand, the overhead transmission lines in electric locomotive has relatively low running cost and high capital cost. We have to erect the transmission line. So, we can choose actually the between the electric locomotive or diesel electric locomotive.